Thank you. Thank you, Krista, for the introduction. Yeah, so today I want to talk about one of my previous work there, my PhD called Alpha Potential Game. Essentially, we use this framework to study the multi-agent reinforcement learning. So this talk will mainly based on the following works, especially the first one. And okay, let me start with some background and motivations in the multi-agent reinforcement learning, and also the dynamic potential game that is related to the to this work. And then I will introduce about our framework, and what is this alpha potential game framework, what is its alpha, how to find it through some optimization framework, and also some algorithm and Nash regret analysis in the multi-agent reinforcement learning. Eventually, I will give you more concrete examples to apply this framework. Okay. So when we talk about reinforcement learning, we know that there's one agent learn to make decisions in this unknown or partially known environment. And this agent has their own goal to, for example, maximize her own utility functions in a long run. And for multi-agent reinforcement learning, you essentially just extend this reinforcement learning framework to n players, where these n players, they kind of interact with each other in this shared environment. And each of them want to maximize their own reward, their own utilities. So it's sort of like a shared environment, but they have some competitive setting in this case. For example, in the autonomous driving, you want to move to your own target as probably as soon as possible. But and for the action, the competition is more obvious here. Like each of them have your own target and your own strategies, and you want to realize your own target. So when we think about the competitive games, a very commonly adopted concept is this Nash equilibrium. So it refers to a set of strategies that, given the current strategies of all the players, if I look into the strategies of all of you, I notice that I wouldn't want to change my own strategy because I cannot further improve my cost, my utility. And it's same for each of you. And this kind of create this sort of equilibrium that no one wants to change anymore. So that is basic idea of the Nash equilibrium. And this Nash equilibrium is known to be, in general, hard to analyze and solve because of the interdependence among all the players here. And some classical work, existing work related to some classical work to solve for the Nash equilibrium, including the mean field theory, like mean field games, assume that every player here are identical. We have the same utility function, and now you only need to focus on one of the representative player. And you assume that there are many players, the n is go to infinity. Now you will have a mean field approximation. And also some recent works on graphon games, but more or less they focus on the asymptotical behavior when n is quite large. So our question here is that we want to target about finitely many players and possibly with heterogeneous players. So players are different. They can have different reward. They have different state transition structure, different action set, and so on. So how to analyze it in this case? And also beyond looking just at the number of players here, can the other game structures like the state transitions or utility structure, can the other game structure influence your learning dynamics when you're trying to find the Nash equilibrium? So that is some key questions we try to answer in this work. Okay, so let's start from a simple motivating example here. So now we consider a case that, for example, there are 4 resources, 4 facilities, and a group of players, they are trying to choose several resources. And each player can choose some subset from this resource, and the cost of using each resource depending on how many other players are using that. So that sort of congestion game you can think of here. If there are many players here, you probably will have like a bad utility in some sense. So that's why sometimes it's called congestion game. So here it's like a static game. It means that we just play this game one time, and that is okay. There's no state at all. Just use your action and get your reward. And if we formulate it a little bit more formally with mathematics language, we have n players, and we have a set of m resources, and your action. You are taking your action AI in a set where it essentially just a vector denoting which resource you are using. And I use this notation to denote the joint strategy profile of all the n players. And this notation throughout the talk just denoting the joint strategy profile of all the other players except player I. Just some standard game theory notation here. And this CR denotes the cost function for using the resource R. So it's a function from like the number of a player to your cost. And W here is just a counting function. Under the current joint profile of all the players, how many people are using resource R? Just count the number. And under this setting, the utility function for the player I, given the joint profile of all the players, is just iterate over all the facility that player I is chosen. And this one, the CR, which is the cost of using facility R, and depending on just the number of the player which are using it. That's just a basic games, the congestion game setup. So I want to mention here why I'm giving this motivating example is mainly because this congestion game actually has a very nice structure. So if we construct the function phi in this form, it seems a little bit artificial, but essentially you kind of sum over all the facilities and kind of doing sort of discrete integration with respect to the cost function of the facility of each facilities. So with such a construction of the function phi, which I call it potential function, you can verify very directly just through very basic computation. You can verify it has this structure. That if you use that phi, change the AI prime and get the difference, this difference equal to the difference in the utility function for each player. So why this structure is so nice and so important here? So let's think about for example, if the current A profile here is already the optimizer for the function phi, for this common potential function phi, then what happens? If I change it into AI prime, you will have a worse value. And this one equals to the case in the UI here. So the player I wouldn't want to change into AI prime as well because of the equality here. And it holds for all the players. Now what happens? No player wants to change anymore. It is a Nash equilibrium. So why this congestion game is so nice? Essentially just because there exists such a potential function such that this structure holds and the maximizer of the potential function is the Nash equilibrium. In that sense, when we want to find the Nash equilibrium, we only need to optimize over one single function. So actually in this pioneer work by Mulder and Shapley, they proposed this this definition called potential games, which they say that a game is called potential game if there exists a function phi such that this structure holds. Then such a game is called potential game. So this is a popular game framework with heterogeneous players because we only require this structure holds. So the UI and UJ could be different in this case. And because the optimizer of the potential function is a Nash equilibrium, there are many works developed algorithm that with convergence guarantee to the Nash equilibrium in this setting, such as the best response dynamic of fictitious place. Okay, so far we are only talk about static game. we just play the game one time and that is, there's no state transitions at all. So how about dynamic games? What happens if there are now some state transitions in this when we play this game? So let's just make the static congestion game into a dynamic case. Now player still want to choose the facilities, but under some safety constraints, so they do not really want some congestion happens. And if there are too many people using the same facility, the facility will transit into a different state, into a congested state. In that state, you will have much higher cost than in a normal state. So now you the state of facility can change every time at each time step. And this state evolution, depending on the current state and also the action profile of all the players. And each player now, they want to maximize their expected accumulated utility in a long run, which we also called value function in reinforcement learning literature. So in control literature, that is objective function, because value function in control literature is just some optimal one, but it's this objective in a long run accumulated utility. So one of the existing approach to solve the dynamic potential game is proposed by the paper by Leonardo and his co-authors, where they proposed this so-called macro potential game definition. So they consider a setting where we have discrete state dynamics with Markovian transitions and Markovian policy. So essentially just a Markov decision process. And their definition is pretty direct generalization from the static potential game, saying that if your strategy satisfies this structure, if you exist some function phi such that for any strategy you satisfy this structure, then such a game is called a macro potential game. And similar to the static case, any optimizer here is also a Nash equilibrium, and many algorithms in the multi-agent reinforcement learning literature has been working on showing the convergence to the Nash equilibrium in this case. But what are limitations? What are the limitations here? The first case is that most dynamic games with the Markovian transition policies are not MPG. And there are very concrete counterexamples to show that even at each time step, we are playing a static potential game. The overall, the accumulated reward and it's in general, it's not a macro potential game. And because the existence of the state transitions here, it's very hard to verify whether a game is a macro potential game or not, and people do not know how to construct a so-called this potential function actually. Therefore, we want a more general form of potential games to study the dynamic games. Okay, so our intuition is pretty straightforward. So we define this alpha potential game to say that instead of 0 here, we allow some error or gap alpha here. So you will have a little bit flexibility to choose a function phi here to make it bounded by some constant alpha. So in the special case, alpha is 0 is just a macro potential game. But now we allow those flexibilities to study a more general class of games. And such a phi in this case, in order to highlight the dependence on alpha, we just call it alpha potential function. So why this framework is, what is the advantage of this framework? So it is a general game framework that allows us to analyze a much larger class of games. And so far, this definition actually allows for both discrete and continuous time state dynamics. And here I haven't specified the strategy class yet, so it can work with open loop and closed loop in stochastic control and Markovian policy in reinforcement learning. So it's kind of general framework here. And similarly, if we have like an optimizer of the alpha potential function phi, So now it's naturally that this profile is an alpha Nash equilibrium. So it still preserves the nice structure that you can reduce the problems of finding Nash equilibrium into optimizing one single function. So here just some overview of the literature and the position of our research here. So starting from last century, people have been doing on the static potential game and some more recent work on the static near potential game, where they also allow those sort of gaps. And they can show that in the repeated static games, they have algorithm to converge Nash equilibrium with an error like alpha. And more recent works, more multi-agent reinforcement learning works is in the setting of macro-potential games, where with a focus on the convergence analysis of the algorithms, basically. So, but our works here can study a more general class of games. And we also have some recent work on the analytical framework of the potential games in a dynamic and stochastic setting. So instead of MDP here, this part usually considers stochastic differential equation setting. And we have some analytical construction of the alpha potential games. So I will talk about this in today's 4 p.m. math finance seminar, but this is not that talk, this focus of this talk. So let's go back to this part. Okay, now let's move to our framework. So let me briefly talk about the setup for the macro games. It's pretty standard in the multi-agent reinforcement learning setting. So we have like we still have n agents, and here S denotes the state space. So we consider finite state space, and the action set for each player I, and the utility function, depending on your current state and the action profile of all the players. And we have state transitions for the system. So here we consider the strategy side here is Markovian policy. So at each time, this policy, at each time, given the current state, it will give you a probability distribution over your action set. So this is a probability simplex. So at each time S, you randomly sample an AI from this probability distribution on action set. And we have this just denotes a joint policy for all the players and the policies with all the other players except I. And here each player wants to maximize her value function as a discounted sum of all the utilities. And for the Nash equilibrium concept we are considering here is a stationary Nash equilibrium. We are given this profile. You basically, whenever you change your own policy, you cannot get a better value function. And in this case, in the Markov games, because of the underlying state transitions and dynamic interactions, and also possibly decentralized decision-making nature, it's actually very hard to solve for those kind of the Nash equilibrium. Okay, so here is our framework to study Markov games. So before during the introduction, I just saying that we want some phi minus v prime smaller than alpha but here in the macro games, we actually can make it into a min-max problem. So essentially we iterate over a function class, and we want to find the best function that give you this as small as possible alpha. And this function class is just take a general class of uniformly epicontinuous function just in order to basically ensure the existence of the optimizer here. So the first result is to say that there exists a function phi such that the smallest value can be achieved. And when alpha is 0 in this definition, it is just a macro potential game. So as we propose this framework, using the min-max optimization to study Markov games, there are two questions we want to answer here. So first, how large is alpha, right? We need to know how large it is. So next, I'm going to show how to find the proper upper bound of alpha for any Markov games through a optimization technique. And once we know the value of alpha, eventually we want to find the approximate Nash equilibrium. The next question is that how to find the Nash equilibrium policy. So I will show the result of two algorithms based on the policy gradient and best response and provide their non-regret guarantee. Okay, so now let's look at the first question, what is alpha? So here we can rewrite the min-max optimization problems in this form. So we have this upper bound y here, and we want to find the y that as small as possible over all the possible phi function in the function class. But here, the decision variable phi here is in a function class, so it's kind of large and hard to do the optimization. So can we find a smaller class for this optimization? So here we provide a relaxation on a smaller function class. This f tilde, this smaller function class f tilde here is composed of all the functions in this structure. So now instead of looking for just for some function in a equicontinuous function class, now we only need to focus on this structure, and essentially for each function psi here, you can find a small function phi just defined on the product space of state and action, but because both of the state and action space are just finitely many dimensions, so it's reduced the problems from a function class essentially into looking for a matrix. Because as long as you have this phi, you immediately got this function. Yeah.
Question. So indeed, state actions are finite, but the set of Markovian policies is still infinite, right? Because you can every time like consider a policy that suddenly chooses a different action and then later times them. Right?
Yes.
Is that a problem?
So it's I'm about to talk about the next page. Yeah. Any other question? Yeah, next question, but I'm going to talk about the problem pi here. Okay. So I want to introduce a technique called state action occupation measure here, where this just denotes like on average the probability that you visit S prime and adopt the policy A prime under the and adopt the action A prime under the policy pi here. And with this representation of state action occupation measure, we can rewrite any function in f tilde with the state occupation measure and the phi here. So in the case that, suppose the case that we know all the state transition, we know all the P, and we know all the utility. So suppose that environment is known here. Your state action occupation measure is known. And this phi is your decision variable that you are trying to find. And for the value function, similarly, we can also write it with the occupation measure, but now it's with the utility function. And now the relaxation problems in the previous page can be rewritten in this equivalent form with the occupation measure here. And now your decision variable here is the small phi, which just taken value on the finite space. But just like your question mentioned, here we actually have infinitely many constraints because we iterate over all the possible policies. So very nice point. So this is a so-called infinite, semi-infinite linear programming because overall it's kind of linear, but we have infinitely many constraints. That's why there's a semi-infinite term here. And there are some a line of literatures just to develop the algorithm approach to solve this, to solve such a semi-infinite linear program. So we actually just applied their algorithm basically. Okay. So far we have covered about how large alpha is, and the next part is to show some algorithm to find the Nash equilibrium policies for. So here we are looking for some performance measure called Nash regret, which is a widely adopted measure in multi-agent reinforcement learning. It's a regret term, which takes the average deviation of the algorithm from the Nash equilibrium. So basically, if we look at each Ri term, each regret at each time stage, essentially it's just measure that here pi t is your current policy of the algorithm, how much you can improve from the current policy. So that is your regret. So yeah, in a special case that, for example, if you achieve the Nash equilibrium, then of course this term is just zero. So the algorithm performance measure is just to minimize the Nash regret. Okay. So our first algorithm is a policy gradient-based algorithm, essentially from the Xinyu and his co-authors' work on the macro potential game. So the update of the policy is pretty straightforward. It's just a projective gradient ascent onto the policy space. So here, this Q bar is the average of the a standard Q function, state action function, where you take the expectation over all the other players, So why I just want to talk a little bit about why it is a variant of a policy gradient, but we actually using the Q function here is that they shown that the partial derivative of the value function with respect to the policy is actually in this form involving this Q function. And that is a state occupation measure. So one of the advantage to ignore this part is that in some case under the pi, the state visitation of some S may be very small, but you ignore that you ignore this part, you kind of encourage exploration to all the S. Okay, so with this algorithm in the alpha potential game, we can provide this Nash regret guarantee. So when t, your training time goes to infinity, then this term just disappears, but we also have a term that cannot vanish due to the game structure alpha here. And the second algorithm is based on some best response idea. So here, for some technical reason, we consider an entropy regularized version. So this part is just the entropy regularization. And we have a regularized value function, Q function, and averaged Q function. And here, we consider the maximum improvement of the smoothed Q function in comparison to the current policy. So given the current policy, how much you can improve, what is the best pi that can give you the maximum improvement in this case. And here is just the idea of the algorithm. So we choose the player. We choose a player and the state that can give you maximum improvement. And we only improve this player's policy at this given stage using the one stage best response. And repeat these steps until no further improvement can be done, and then return the policy. So yeah, so this is the second Nash regret bound for the best response-based algorithm. And we also have this one term disappear as the training time goes to infinity, but some term regarding to alpha about the game structure that cannot vanish here. Okay, so finally, I want to talk about, just give you some examples how to use this framework to study a more concrete game. So let's go back to the dynamic congestion game I gave in the motivation. So like in the static game, each player chooses some subset and the cost depending on the number of players using it, and there's no state transition. And now the Markov congestion game, it just means that at each stage we are still playing the same congestion game, but now we have state transition. And we formulate it is like a similar math formulation. We have n agents, and we also each action is just the vector denoting which resource you are using. And we also have like the aggregated usage of the resource given the current action profile. And now your reward of each player, which is a summation of all the resource you are using. And then here, the reward from each resource also depending on the current state. So that is just a difference from the static potential game we just mentioned. So to analyze this game, like theoretically, what is a reasonable choice for the alpha potential function? So because like each state, it is a static potential function. We have some small phi here. Then our guess is that what about we just consider the expected value of the summation of this static potential function and see what happens. And our results here show that if we adopt such a candidate for the alpha potential function, we indeed have a bound for alpha. And that bound can decrease with respect to the number of players, but can also depend explicitly on some other model parameters such as state space, size, and how many facility you have, and some discounting factors. And this alpha is also depending on the maximum of this function psi here we choose, but we actually show that this one is bounded and doesn't depending on n, so that your alpha will decrease as number of player goes to infinity. So this is the analytical analysis by choosing one candidate alpha potential function. But we actually also use the semi-infinite linear programming and solve it with algorithm. So at least in this parameter setting, we can say that alpha is just almost zero in this case. And finally, some results by the policy gradient and best response I just introduced. So let me explain a little bit what is happening here. So here we have four facilities, A, B, C, and D. And D gives you the most reward in the general case. So players will prefer D over C over B over A. However, if there are more than half of the players using the same facility, the first facility will transit into a very bad state and give you a very high cost. And if you want to transit from a unsafe state, very bad state, to a normal state, there can be no more than 1/4 of the players inside it. So if we focus on this, so this one gives you the how many number of players in each facility under the current state. For example, if we look at the yellow one means that the A, B, C are still normal, but D is in a very bad state. In that case, even though D will give you a high reward, there will be only 2 players in that state to allow the facility to transit into a normal one. And because C have better reward than anyone else, there will be 4 players, which is a half of number of players inside it to get the best reward, and the remaining player are in B over A, because in A you will have few rewards than in B. So despite that it is a competitive game at the beginning, during the training process, the players actually learn how to cooperate a little bit. In this case, to okay. So to sum up, we propose this min-max optimization framework to study general Markov games by quantifying this parameter alpha. And we propose a relaxation problems to bound this alpha utilizing state occupation measure and formulate it into a semi-infinite linear programming problems. And we propose 2 algorithms based on policy gradient and best response, and provide corresponding natural grad guarantees, and finally characterize this dynamic congestion game which is beyond the macro potential game setting. So finally, just some thoughts on the possible future work. So far, this semi-infinite linear programming can only be solved when we know the environments, when we know what is the transition probabilities. But an interesting future implementation will be like, can we do that? Can we solve this semi-infinite linear programming data-driven, like combine online learning and reinforcement learning together, so that whenever we have a Markov games, we can know that what is alpha and what is the alpha Nash policy. So that is something quite interesting here. And also some better algorithm designs, better dependence on the game parameters, and also the local Nash equilibrium analysis, because in some examples that people care about local Nash equilibrium instead of the global one. And also there are some other possible direction is that in the real world, we notice that sometimes the players will stuck in somewhere between the Pareto and Nash. So it's not purely competitive. It's also not purely cooperative as Pareto, but this stuck in somewhere in the between. So in the like algorithm conclusions case. So probably we can use this alpha framework to study like where the learning dynamics actually end in the eventually. And also some like other types of games, but like leader follower games and something else. Yeah. Yeah, so that is basically for today's talk. Thank you.